Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are conducting a deep dive into the practical applications of Gauss's law from Unit 1, Electric Charges and Fields, and we promise you a simple, exam-safe explanation to master this topic. So let's start with a question, something from everyday life. Imagine you're in a car and a big thunderstorm starts. Lightning is striking all around. Why do they say the safest place to be is inside that metal car?
Yes, that's what everyone says. It's very surprising, isn't it? My first thought would be that the metal should attract the lightning. So shouldn't the electric field inside the car be incredibly strong?
Precisely. That's the counterintuitive part. You'd think the metal would concentrate the field. But actually, an application of Gauss's law shows us something fundamental. Inside a conductor in electrostatic equilibrium, that just means after the charges have settled, the electric field is always zero.
Always zero.
Rigorously zero. This is the principle behind what we call a Faraday cage. We use it to shield sensitive electronics, from external fields. Today, we'll see exactly how those charges on the car's surface move around to create this perfect shield, to make E equal to zero inside.
Wow. So electrical shielding is a direct result of applying Gauss's law. That's quite practical.
Absolutely. Now let's get to the core idea. Why do we even need these applications? Gauss's law itself is, of course, very powerful, but its real genius, its utility, comes out when we apply it to specific shapes.
You mean like spheres or cylinders?
Exactly. For things like a charged sphere or a long wire or a large sheet, if you try to calculate the field using Coulomb's law, you have to do some very lengthy calculus.
Right, that integration over continuous charges, top to bottom, it's very tedious.
And very easy to make a mistake in an exam. So think of it this way. Coulomb's law with integration is like a general-purpose screwdriver. It works, but it's slow. The applications of Gauss's law are like a specialized toolkit. A tool? Yes. You have a sphere tool, a cylinder tool, and a plane tool. When the shape of the charge matches one of these tools, the solution is almost immediate. It's elegant.
So the secret ingredient here is the shape, the symmetry.
That's the critical point. The secret is symmetry. Symmetry does all the hard work for us, Gauss's law just extracts the final answer. So the mental image you should have is this toolkit of imaginary surfaces. We call them Gaussian surfaces.
Imaginary surface.
Yes, completely imaginary. For a spherical charge, you imagine a spherical surface around it. For a line charge, you imagine a cylinder. For a sheet, a small pillbox, you just match the tool to the problem, and the field just emerges from the symmetry. Okay, now that we know the why, let's get the formal definition right. Could you read out the definition of Gauss's law from our source document?
Of course. It says, the total electric flux through a closed surface is equal to the net charge enclosed divided by the permittivity of free space, epsilon zero.
Excellent. Now, that math, the integral of E dot dA, what does it really mean in simple terms?
Yes, that is a bit daunting. What is this flux exactly?
Flux is just a way of counting. It's basically counting how many electric field lines are passing through your imaginary surface.
So it's about the flow of the field lines.
Exactly, the flow. And this gives us a simple 5-step method for solving problems. Step 1, identify the symmetry. Is it a sphere, a line, or a plane? Step 2, choose a Gaussian surface that matches that symmetry.
A sphere for a sphere, a cylinder for a line.
Got it. Step 3, calculate the net charge enclosed, the Q enclosed inside your imaginary surface. This is a crucial step. Step 4 is where the magic happens. The symmetry makes the scary integral just E times area.
Oh, so it simplifies that much?
That much. So you just set E times area equal to Q enclosed divided by epsilon naught. And finally, step 5. You just solve for E. It becomes simple algebra.
No complex integration needed.
None at all. And this process gives us 3 essential results you must remember for exams. First, for a uniformly charged sphere, when you are outside it, the field drops as 1 by r squared.
Like a point charge.
Exactly like a point charge. From far away, a sphere looks like a point. Second, for an infinite line of charge, the field drops slower. It goes as 1 by r.
That's interesting. Why slower?
Because the charge is spread out along a line, so the field lines spread out less, you could say.
Okay, that makes sense.
And the third one is the most unique. For an infinite plane sheet of charge, the field is constant.
Constant. It doesn't depend on distance at all.
Not at all. E is just sigma over 2 epsilon naught. It's a uniform field. This is a very important result, especially for capacitors later on. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, let's try a quick conceptual example, one that often causes confusion. Imagine a solid, non-conducting sphere. An insulator. It has charge spread uniformly through its volume. Where do you think the electric field is the strongest?
My first guess would be at the center, maybe, where all the charge is sort of concentrated around. Or wait, because of the car example, maybe it's zero inside, like a conductor. I'm a bit confused.
And that is a very good confusion. This is where students lose marks. You're mixing up a conductor and an insulator. The key is the material type. For an insulating sphere, the field is absolutely not zero inside.
It's not.
No, in fact, inside the sphere, as you move away from the center, the field increases. It increases linearly with distance. E is proportional to R.
It grows.
It grows. But once you get outside the sphere, then it starts to drop, following the 1/r² rule.
Ah, I see. So the field is actually strongest right at the surface of the sphere.
You have got it. The maximum is at R equals R. Inside, there isn't enough enclosed charge yet. Outside, the distance effect is too strong.
That's a critical distinction.
It is, and understanding these field patterns is vital for the next topics, like electric potential and capacitance. You need these fields to calculate those. Okay, now let's talk about 3. Silent killers. Common mistakes that cost marks. Misconception number 1 is the universal fallacy. Many students think Gauss's law only works for perfect spheres or lines.
But you said it was universal.
Exactly. The law is always true for any shape, any charge. But it's only easy to solve when there's symmetry. That's the key. So the hook to remember is Gauss's law is universal. Easy application requires symmetry.
Okay, got it.
Misconception 2. The conductor confusion, which you almost fell for. Assuming the field inside any sphere is E equals 0.
Right, I did think that.
Remember, E is 0 inside only for a conductor in equilibrium, because in a conductor, charges are free to move and they rearrange to cancel the field. In an insulator, the charges are stuck.
So for an insulator, E is proportional to R inside.
Perfect. So the hook is insulating sphere, E inside proportional to R, conducting, E inside equals 0. Now the third one, this one is tricky, the irrelevant charge. Students think that charges outside the Gaussian surface don't affect the electric field E on the surface at all.
But wait, the formula only has Q enclosed, so why would outside charges matter?
This is a subtle trap. It's the difference between the electric field E and the total flux. The charges outside absolutely do affect the electric field vector E at every single point on your surface.
They do.
Yes, the E field at any point is the sum of the fields from all charges inside and out. But, and this is the beautiful part of the law, their contribution to the total flux over the whole closed surface is exactly 0.
How is that possible?
Think of it this way. For an outside charge, any field line that enters your surface on one side must also exit on the other side.
Ah, so the influx and the outflux cancel perfectly.
Precisely. So they affect the local field E, but their net flux is 0. The total flux only depends on what's trapped inside.
Okay, that is a very important distinction to remember. The local field versus the total flux.
Yes. Now, to help lock all of this in, let's use some memory anchors. For the steps, just remember the mnemonic SAG.
SAG.
S for identify symmetry, A for apply Gauss's law, and G for get the field, SAG. And a simple phrase to keep in mind is, match symmetry to Gaussian surface, let Gauss's law extract the field.
That sums it up nicely.
And one more thing, a physical gesture. When you're studying, actually use your hands. Make a sphere with your hands for spherical symmetry. Roll your hands into a cylinder for cylindrical symmetry, and hold your hand flat for a planar surface. This connects the concept to a physical action in your brain.
A bit of muscle memory. I like that.
Exactly. So, to summarize our deep dive today, let's boil it down to 3 key factual points for your exams. First, Gauss's law is an elegant shortcut to calculate electric fields for symmetric systems like spheres, lines, and planes, and it lets you avoid difficult integration.
The specialized toolkit.
Second, the field's dependence on distance is unique for each shape. It's 1/r² for a sphere outside, 1/r for a line, and constant for a plane.
Those 3 results are key.
And third, the law explains real-world phenomena like electrostatic shielding, where a conductor rearranges its charge to make the electric field inside it exactly 0. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us in this deep dive. We wish you the very best for your studies.